Hi, so we've talked about heat, and we've talked about the relationship in between heat and temperature, and we've let things come to equilibrium and done some calorimetry problems, but so far we haven't talked about precisely how heat is transferred in between objects. Thus far, I've just drawn objects, and then gypsy magic occurs, and somehow the heat pops from one to another, and then they achieve thermal equilibrium, where TA and TB become equal. And it turns out that, in fact, you don't even need to touch these objects together, and you can have heat transfer at a distance. We'll talk about two of these three things in a little bit of detail, at least give you a model for each. But the short story is that there are three ways of doing heat transfer. There's conduction, which is putting them together and allowing the individual collisions in between atoms and molecules to do their thing. There's convection, which is really a process for liquids and solids, liquids and gases, where I don't want to wait for the molecules to bump into each other. I'm just going to mix them up and then kind of shuffle them together to get my statistical average. And then finally, there's radiation. And that's the spooky action at a distance one, where the hotter object will basically win this photon kind of push of war and irradiate the other one with more photons than it receives. So these two will give you a little toy model that you can use. This is great, this is pretty good, so you could use this for some engineering applications. Our thermal conductivity model. We won't talk about convection more than qualitatively, so I'll just say it's a thing that exists. So the first mode of heat transfer will be conduction, which on a microscopic level is literally just, the way that agitation in a moss pit might propagate from one side to the other, something like that. There's one really shovey guy, and then, that propagates outwards. So that's just like molecular kinetic energy transferred by collisions. And the important part is that in order to collide, you got to be touching. So imagine that I have an isolated metal bar out in space or in some sort of thermally isolated bag, and I really heat up this end, and this end is still pretty cool. So the hot end eventually will have exhausted all of, so the hot end will start with molecules that are moving quite a lot. And then at the cold end, the molecules might be moving a small amount. And if I were to draw this graphically, we would call this before and after maybe. So we'll have length and temperature. And who knows, these are probably not absolute units. So we'll have our before. And we'll heat up one side of this, and we'll leave the other side cool. I don't think the green shows up too well, but that's fine. This isn't really precise. Okay, so we heat up that side, and then what's going to happen is the hotter molecules will bounce into the cooler molecules, and afterwards we'll get, along the length of the bar equilibrium. So what you would call local equilibrium. So everywhere the same. Okay, so this is both of these actually are wonderful opportunities to kind of think like a theoretical physicist. And we'll write down a formula that has all of the good features that we want it to have and works well enough. So what on earth, and I think we kind of did this before at least once with thermal expansion, or the forces associated with thermal expansion. So I want to know how fast this thing's going to come to equilibrium, or how much time it's going to take for the hot end to communicate with the cold end. And I'm actually going to kind of make a slightly simplified system, which doesn't seem like it's going to work as well as it does, but it works pretty well. So I'm going to have, put that in red, a hot and a cold reservoir. And what reservoir means is it's basically so big that its temperature is never going to change. So I can let all the heat that I want to come out of the hot side, and it's never going to actually increase the temperature of the cold side. So it's really just a mathematical statement of these things are really big. And I'm going to connect them with a pipette or a really thin bar. And this really thin bar is going to be the thing that conducts the heat. So the bar is the thing I care about. And this somewhat artificial setup lets me write down a formula that makes a lot of sense. So what I want to talk about is the heat transfer per time. And because heat is energy, that would technically be a power. Q is always kind of delta Q, so this would really be Q over delta T. So basically the joules per second that's going to flow from the hot side to the cold side along this bar. And if you think about it, it really is the same sort of question. It's just we're using these things, reservoirs, so that we don't have to keep constantly updating our formula because, as this thing gets colder and that thing gets warmer, there's going to be less heat transferred in between them. And I already gave away one of the things that this could possibly depend on. Okay, so this is how theoretical physics works, is you draw a cartoony picture, you stare at it for a while, you write down what the answer could possibly depend on or the formula you're looking for, and then you say voila and go like this and have experimentalists investigate this. So what on earth could this possibly depend on? The rate that heat is transferred from here to here. So one thing it could depend on, we just said it, so we may as well say it, is the temperature difference. And so mathematically that would be TH minus TC or delta T. What else? Maybe pause and test your mettle as a theoretical physicist. Okay, so I'll use the same notation that Gene Colley does. The length in between them, the longer the length of the bar, the less heat's going to be transferred, maybe. What about the area? The bigger the area, so imagine instead of one of these wires connecting the two, I had two, so twice as much heat could be transferred, so this has got to depend on the area. And then finally, vaguely, we have material properties, which I really apologize for, are denoted with the symbol K in thermal conductivity. So we're really giving K a workout in this class. We'll just say properties. So we have material properties itself, like if this is a metal, it's going to be really good at conducting heat. If this is Pyrex glass or styrofoam, it's going to be terrible. So material properties are important. And that's denoted by this lowercase k. Again, I apologize. What else could be important? The length and the cross-sectional area. And we'll call that capital A. So now the question is, how could I possibly arrange these? Oops, I did. Yeah, we'll leave it as L. So how could I possibly arrange these so that they're in the right order, upstairs where they need to be upstairs and downstairs where they need to be downstairs? And then this will be our formula. And it turns out, this works pretty well enough. So change in, or temperature difference. The bigger the temperature with more power or less power. I think more power. So that should be upstairs. Material properties, that's just going to go out in front because, what we're basically doing is defining bigger K means you're better at conducting heat. That'll be the thermal conductivity. What about length? Longer the length, easier or harder it is to conduct heat? Yeah, so that goes downstairs, and then bigger cross-sectional area. More lanes on the highway means I conduct heat faster. So this is it. This is our formula and model for thermal conductivity. And that is exactly what this thing is called, the thermal conductivity. And again, it's not Boltzmann's constant K. There's just more physics than letters, so that's a different K. And we can come up with the units of K. So specifically the SI units of K. So the units of the left-hand side, which is joules per second. So power is energy per time. That's always joules per second, which is watts. And then that's equal to the thing that we're looking for, the units of K. Units of A are meters squared. Units of L are meters. And that is Kelvin or Celsius, again, because we have yet another delta. It's ambiguous. We could use Kelvin or Celsius. I'm going to use Celsius because there's too many K's in this already. All right, and then that can simplify. And therefore, we have the units of the thermal conductivity in SI, or SI-ish, are watts per meter degree Celsius. Okay, so this is how you would use one of these, is you basically look it up and then you use this formula, the conductivity formula. We'll do something that's realistic in the sense that it'll give you a sense of, on a cold day, just how much thermal energy can flow out of something. And it's not realistic in the sense that this isn't a really good model for glass windows in a house, but it turns out this formula is good enough. And this is a bit open-ended, so we'll define what we mean by things by like cold day. So let's say you've got the interior of the house at room temperature and the exterior is like 5 degrees or something, so that's pretty cold. So we'll call T inside or T hot 20 degrees Celsius, T cold or T outside, we'll call that 5 degrees Celsius. And then what I would have to do is look up the properties of the window itself. So let me just make up some. Let's say the length of the bar. So what this would really be is the thickness. So to the best of my ability, I will draw this pane glass window. So that would be L. We'll call it 3 millimeters. So we'll say they're pretty cheap and thin. And then A would be the area, so that would probably be a couple of meters squared. So let's say it's a really thin, really big window. So we'll call that 3 millimeters, call this 4 meters squared. Just throwing a curveball with the units because that's how this is going to shake out. And what I would have to look up is K for glass. So the thermal conductivity for glass. And it turns out that's about 0.84. You will more likely than not see these in degrees Celsius versus Kelvin because this is more of an engineering unit, and engineers don't really care about our absolute units. Shameful. So then I'll just call it power. It's heat power, so it's Q over T. 0.84, everything's in SI, so that's great. Meters degrees Celsius. And then, just kidding, not everything's in SI. I got to put that in SI. 0.003 meters. And this is where the trouble starts. And then delta T would be 15 degrees, because the inside interior is 15 degrees Celsius hotter than the exterior. And this term gets pretty big, so you get something like 16 kilowatts, 17 kilowatts, holy heck. Okay. So that's about like 4,000 times 4, so that's about 4,000 nutritional calories every second. So that would be, like a bite of food. So if you've ever had somebody in your household get upset about leaving windows open in winter, they were completely within their rights to do so, because that actually is like quite a lot of energy. Okay, so that's by conduction, and that's literally like kind of molecules elbowing each other, and this constant basically tells you how good the molecules and whatever the material are elbowing each other and transferring heat by collisions. So the next of the three ways we have to transfer heat is the one that we just like basically won't talk about at all, aside from letting you know it exists, because there really is no even simple model that even sniffs like enough math to be useful, because what convection is literally the flow of whatever. And so you'd have to know the specific details of like how, air flows, or how the fluid flows, or how the plastic in the Earth's mantle flows, if you're talking about the mantle convection. So we'll just say it exists. And explain why it's pretty good at what it does. So now let's say that I have some hot stuff and some cold stuff, and they're side by side. Right, so here's the color coding them is great. So, it's kind of funny though, is like I have no idea why blue is cold and red is hot, or I kind of like lost the historical memory of it, because in astrophysics a red star is cold and a blue star is pretty damn hot. So blue hot is actually hotter than red hot, so at this point it seems like weird to me to do this. Okay, so now what I'm going to do is, instead of these are two blocks that are solids that are touching each other, imagine this is liquid or gas, and they're just able to kind of like flow around each other. And the details of how they do that, again, depend on exactly what it is. But let's say that, I literally just kind of like chop them up. And I have alternating blocks of hot and cold and hot and cold. And what I've done, it doesn't seem like much, but I've actually facilitated all of these other processes. Whoops, yeah, that's exactly what I meant. Cold is not red. So radiation, which we haven't talked about yet, and convection that we have, all of a sudden I have what used to be this much surface area of contact. Now by like letting them flow around each other, I've let this much surface area be in contact. It's much more. So these alternating packets of hot and cold will equilibrate much, much faster than they would have otherwise. So basically chop the stuff up, let it flow. What you'll get is a hugely improved rate of coming to equilibrium if you do this. So that's all we'll say, is that this happens all over the place. So in biology, you have blood circulation. So part of the reason you circulate blood is, nutritional and to oxygenate cells, but it's also for thermal regulation. So you do this. There are processes in the Earth's mantle and atmosphere, so atmospheric currents. If we didn't have atmospheric and oceanographic currents, we would have much chunkier temperatures, which would not be good. And then we do this on purpose in an engineering standpoint with air conditioning, of course, and radiators in cars. So what a radiator does is basically circulates the fluid so it picks up, heat and then goes and spits it out to the atmosphere. So that's just a process. Again, you got to know, if it's a fluid, you would have to know the relevant laws of fluid flow, which are really grubby. So we'll just say that that's a thing. So the last way of transferring heat, and in my opinion the coolest, is the magical one. So the thermal conductivity of vacuum, like space, is 0, right? If there are no molecules, there's no way of transferring energy. So for instance, the sun does something to us and because we're in space, we use Kelvin. On Earth, you tend to use Celsius. How on earth is the sun heating us up? So obviously it's not conduction. It's not convection either. It's not like a chunk of sun stuff is coming and mixing in with Earth. It's got to be the last thing, which is radiation. And radiation is the transfer of heat by photons. So packets of light. Light carries energy. Hot things emit light. So the whole story of packets of light we may or may not get to in this class. But this is how things work, is that hot things emit light. Light travels through vacuum and carries energy. And absorbing light will jiggle your molecules. And to really put a fine point on it, jiggling molecules is temperature. So that is the definition of temperature. So we do have a pretty good mathematical model that we could use for this. And this kind of came a little bit from empiricism, which is to say just observing how things actually behaved. But you can make one of these arguments like we made with conduction a bit. But give me a thing, right? And this thing is hot, it's at some temperature, and it's emitting photons. So let's say it's red hot, okay? So if I show you a picture of a red hot thing, can you tell if it's hollow? Probably not. So in fact, what's going on the inside, like all things that have the same surface area and the same temperature, because the photons are leaving the surface, so that's all we care about. And so what you get is power is proportional to surface area, which I'll just denote SA. And then, of course, it's got something to do with temperature. This is the empirical part. Turns out it's temperature to the 4th power, which is kind of bizarre. And I'll live my dream and have blue photons coming out of this. So this is a star, and this is really hot. So the idea is that the photons only either scatter or are emitted from the surface itself. You don't know what's going on inside. So that's why only the surface area is important. Okay. So it turns out that there are a couple of other parameters. One is kind of empirical. Different things are better or worse at emitting and absorbing light. So if this was maybe like black Kevlar or something like that versus a shiny mirrored disco ball, it would actually behave a little bit differently in terms of reflecting and absorbing light. So there's a constant, it's kind of like a BS constant. It's called emissivity. And emissivity is this fudge factor that basically depends on how shiny you are. So emissivity of 0 is what's called a black body. Sorry, emissivity of 1. That's crazy. which means you're a perfect emitter. And an emissivity of 0 would be that basically you never emit a photon. And ironically, the term blackbody seems a little bit weird, is that if you're perfect at emitting light, you're also perfect at absorbing light, because these processes kind of go in both directions. So quote unquote blackbody doesn't mean the thing's actually black. So for instance, stars are perfect black bodies, just about. And equals 0, the opposite of a black body would be something like a disco ball, which is like perfectly reflective. So if you have high reflectivity, it tends to make your epsilon emissivity lower. So that would be something perfectly reflective. Okay, so we get one kind of fudge factor that has to do, so I guess it's not, in the sense that it's like K. In thermal conduction, it's some characterization of the material. But with that, we get radiated power, P again. So this would be the amount of heat energy emitted by this thing. So that we're talking about emitting. So Q in some amount of time. There's our fudge factor, which has to do with how shiny you are. There's another constant called sigma to make all the units work out. This is a universal constant. The material properties are all encased in epsilon. And then there's A for the surface area, T to the 4th. Okay. So this sigma thing, it's pretty easy to remember. It's 5678. 5.67 times 10 to the 8th. And if you worked out the units, you would get watts. So we need watts. But then we have meters squared downstairs and Kelvin to the 4th. So this could be degrees Celsius to the 4th as well. And this is what's called the Stefan, make sure I spell Stefan right, one N, Boltzmann constant. As opposed to just the plain old Boltzmann constant, which is K. Sure. Okay, so we'll show how to use this once, and basically those two things are all we'll talk about with, conceptually you should know how heat is transferred by any of these three processes, but mathematically we'll just talk about radiation and convection. So let's actually do this for the sun. So how many watts do you think the sun is pumping out? Probably a few. Okay, the important part is, well, so clearly this is absolute temperature, so there was no C there. This needs to be in Kelvin, so it's not like ice is not emitting photons, it actually is. So this is an absolute, no delta there, so you really do need to use K. Okay, so the interesting thing is that this is the surface temperature only. Whatever's going on in the interior of the sun, just like all we care about is its surface area, we only care about its surface temperature. And that's 5,800 on average degrees Kelvin. Absolutely, again, no delta, we can't get away with using Celsius this time. So, the party's over. What else do I need to know? I need to know the area of the sun's surface, the surface area. So that would be 4 pi radius squared of the sun's surface. So I would need to know the radius of the sun. The radius of the sun is pretty big. So that's 7 times 10 to the 8th meters. And then I would need to know that the sun is a perfect black body. So that would make its emissivity constant 1. And the default assumption is that if somebody doesn't tell you what the emissivity is and they don't say it's reflective, you can just use emissivity of 1. So then we have everything we need. So we have the power emitted by the sun is 1 times 5.67 times 10 to the 8th gross units, meters squared. Kelvin, got to be Kelvin to the 4th power. 4 pi 7 times 10 to the 8th meters, quantity squared, and then 5,800 4th. And you can already tell this is going to be a pretty wild number. So 4 times, put in 1 sig fig there, so only 1 sig fig there is enough. 4 times 10 to the 26th watts. But shouldn't be that much of a surprise that the number is, but astronomical. Yeah, people would call this like 1 solar luminosity. Okay, so last teeny tiny little comment about kind of statistics and what this means. So let me go back to this scenario where I have 2 things coming to equilibrium, but they're air-gapped, they're not touching. And I'm letting them come to equilibrium with radiation only. So I've got my TA and my TB. And then I wait, and finally they're at equilibrium. Does this mean that they've stopped exchanging photons? No, because any temperature they're at, above absolute 0, which is to say any temperature they're at, they are going to be emitting power. So in a sense, what thermal equilibrium for radiating object means is that the photons are balanced. Is that statistically average, and there's a just disturbing number of individual photons that are being, exchanged by these things, is that the flux of photons from A to B equals the flux of photons from B to A. So, it's not that they've stopped. And likewise with conduction, it's not like there are no more collisions in between molecules. It's just like the statistical averages have equaled out, and they're in a statistical form of equilibrium.